Projectile motion, two-object pursuit, gravity, circular motion, and a lot more are all described by kinematics, which for our purposes is basically the math of how things move. We'll start with an object that can only move in two directions, forwards and backwards. Now to keep track of its position, we'll just call this the x-axis, and then its location is just a number, which corresponds to the x-axis value of its position. Specifically, we'll say that its position is at the center mass, which is basically the point where the object would balance if you were to hold it just there. So kind of like the middle of the object. Now what happens if I take this object and I move it to the right? Well, we could say that it's moved some number of units to the right, but to be more precise, we can measure its final x position and its original x position and subtract the two. Doing so gives us the object displacement, which is basically how much it's moved in a certain direction. But to really talk about how things move, we have to introduce time into the equation. The faster something's going, the less time it takes for a certain amount of displacement to occur. So we divide by the change in time, and that gives us velocity. So if we move 5 meters to the right in 2 seconds, then our velocity is 2.5 meters per second to the right. If we want the exact velocity at some single instance in time, then we just need to take the limit as our time step gets infinitesimally small. In other words, take the derivative of position with respect to time. Now since velocity is the ratio of two changes, we can also show it as a slope, where the vertical axis represents the object's position and the horizontal axis represents time. So over time, we can see the object's position, and the slope of this graph will tell us the object's velocity at that point. Now if we want to fully describe the motion of objects, we'll also need one more quantity: acceleration. Acceleration is like the velocity of velocity. Basically, it's just the change in velocity over change in time. So when you go from a low velocity to a high velocity in a short amount of time, then you have a high acceleration. Now to get instantaneous acceleration, we again just take the limit as our time step goes to 0. And just like the position versus time graph, we can also find the acceleration versus time graph from the slope of the velocity versus time graph. Man, that's a lot of graphs. Now it's time to put some equations to this. So we know that the average velocity is the change in position over change in time, which is the same as the current position minus the initial position over the final time minus the initial time. It doesn't matter what we decide to let our final time be though. It could be 0, 2, 500. As long as we're consistent, then the change in time will be the same. So because of this, we'll usually let our initial time be equal to 0, so then it drops out of the equation. Now we can multiply across the final time and add across the initial position, and we'll get the final position is equal to the initial position plus the average velocity times the change in time. And since position and velocity have the exact same relationship as velocity and acceleration, the same equation is true for velocity and acceleration. But what if we have both acceleration and velocity? Well, remember that the slope of position is velocity, and that the slope of velocity is acceleration. This also means we can get velocity from acceleration times the change in time, or position from velocity times the change in time. If we assume constant acceleration, a, then our velocity is just the acceleration times the change in time, plus a constant c. Plugging in t equals 0 shows us that the constant c is actually just the initial velocity, which we'll write like this. Now we can go from velocity to position in the same way, and once again, the extra constant is just our initial position. Now we have a parabola describing the object's position, velocity, and constant acceleration. And it turns out that for human-sized objects near the surface of the Earth, gravity acts with basically constant acceleration. If we plug this into our equation, we can model the height of an object over time. So for example, let's say we drop an apple from 100 meters off the ground with no initial velocity, so we don't throw it up or down, and we'll also go ahead and ignore air resistance. How long does it take for the apple to land? We'll say that the apple starts moving at time equals 0, and we're given the initial velocity and the initial position, and we know gravity. Since we want to know when the apple hits the ground, we'll set the y position equal to 0, which is the height of the ground. Now we only have one unknown in this equation, the time. And solving for time gives us this. Now if we plug in the known quantities, we get 4.52 seconds. We know our time will be in seconds, not minutes or hours or something, because our acceleration is also given in terms of seconds. Likewise, if we have two objects with their own initial positions, velocities, and accelerations, then we can model their position over time. If we want to know when an object in pursuit will reach another one, then we just set these two equations equal to each other and solve for time. So when the two position curves cross, they're at the same x position at the same time. But what about objects that move in more than one direction? In that case, we're going to need more dimensions to model their motion. So let's start with position. For two-dimensional motion, we'll need two axes and two numbers to represent the object's position, the x position and the y position. To make things easier, we'll bundle these two into the object's position vector, pointing from the origin to the object's position. Notice that this is just a different way of writing the same information, right? We still have the x position and the y position available. Now the reason this is useful is because now when we want to get the displacement, we just have to subtract the final position vector from the initial position vector. The way we do that is basically just by subtracting each component of the vector, like this. Now for the velocity, again all we have to do is divide the displacement by the change in time, and for acceleration it's the same thing, just divide the velocity by the change in time. Now if you need the instantaneous velocity or acceleration, just take the limit as the time step gets infinitesimally small. Now here's the thing, the x component and the y component of velocity and acceleration are completely independent of each other. If you were to drop a bullet from your hand or fire it from a gun, it would take the same amount of time to reach the floor, because the only difference between these two scenarios is the x component of the velocity. In fact, Mythbusters has done a video on this exact topic, and that makes our life easier because it means we can just solve for the x and y components separately. So let's take the example of firing a cannon. In this case, we're given the angle of the cannon, which we'll call theta, and the initial firing velocity. Starting with the x component because it's a bit easier to calculate, we know that the cosine of the angle theta is equal to the ratio of the horizontal component of velocity, the adjacent, and the total velocity, the hypotenuse. So multiplying this by the launch velocity, which is the hypotenuse, will give us the x component of our initial velocity. Now we're assuming no air resistance here, and there's no wind or something like that, which means we don't have any acceleration in the x direction. We'll also go ahead and say that the muzzle of the cannon is the origin, which means that our initial x position is 0, and so it drops out of the equation. Now for the y component, we have to deal with the acceleration of gravity. The sine of the launch angle is equal to the ratio of the vertical component of the velocity, the opposite, to the total velocity, which is the hypotenuse. So once again, multiplying this by the launch velocity cancels out the hypotenuse and gives us the y component of our initial velocity. The initial y position is 0 again, since we're starting at the origin, and our acceleration from gravity is downward in the negative y direction, so we can plug it in here. Now with these two equations, we could, for example, figure out how far away the cannonball lands. First, we'd use the y equation to solve for the time when the cannonball hits the ground, and we plug that into the x equation, so we know the x position when the cannonball hits the ground. But what if our motion is constrained to a circle? Instead of defining velocity with a velocity vector, we can define it based on how the angle of our position is changing over time. Our angular velocity, omega, is equal to the change in angle over change in time, or our angle is equal to omega times t for uniform motion. Now if we're using radians as the angle system, then the angle theta is defined as the ratio of the arc length to the radius. When the object's moving in a circle, the radius isn't changing, but the arc length is changing by the velocity of the outside object. In other words, the angular velocity is equal to the linear velocity divided by the radius. With these two ideas in mind, we can define the position vector as a radius times either the sine or the cosine of the object angle, which we know is equal to the angular velocity times change in time. Notice that the magnitude of this vector is just the radius. Now we can get our velocity vector from the derivative of position, which looks like this. Now the magnitude is r times omega, which if we rewrite, we can see is just the same as linear velocity, as we would expect. Now lastly, we can get the acceleration from the derivative of velocity. But look what happens if you pull out the negative omega squared. The acceleration is just a negative multiple of the position vector. This means that it'll always point in the opposite direction of the position vector, from the outside of the circle to the inside. Also, its magnitude is equal to omega squared r, which after some rewriting looks like this. This is the equation for centripetal acceleration. Now lastly, we have to talk about reference frames. So far, we kinda just been taking the velocity as an absolute thing, but it's not. It depends on who's observing it. So for example, let's say you're on an airplane going 900 kilometers an hour relative to Earth. From someone standing on the ground, that airplane's going at 900 kilometers per hour. But relative to you on the airplane isn't moving at all. Instead, the Earth is moving behind you at 900 kilometers an hour. Neither of these perspectives are more true than the other. It all just kind of depends on where you're measuring it from. Now, if you're in a car going 100 kilometers per hour in the direction opposite the airplane, as measured from someone standing on Earth, then relative to you, the airplane is going at 1,000 kilometers per hour because we have to add both the velocity of the airplane relative to the ground and your velocity relative to the ground. Because from your perspective, the Earth is going behind you at 100 kilometers an hour. But actually, the Earth is just going around the Sun at like 30 kilometers per second. Well, wait, the solar system is going around the center of the galaxy at like 200 kilometers per second. So which perspective is correct? None of them.